sequences. A sequence is a list of terms which have a special relationship between them. Once the pattern of a sequence has been recognised, it can be used to find subsequent terms, and we already know some examples of those. So the multiples of 3, and we've got the sequence there, the square numbers. So that's 1, 4, 9, 16, 25, 36, and so on. The cube numbers, 1 times 1 times 1 is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed, 64. 125, and so on. The prime numbers, so the lowest prime number is 2, then 3, then 5, 7, 11, and so on. And the Fibonacci sequence is a special sequence which goes from term to term. And it starts off with 1, 1, and the next term is found by adding the 2 previous ones. So 1 plus 1 is 2. The fourth term is found by adding the second and the third. So that's 1 plus 2, which is 3. The next term is found by adding the 2 previous ones, so 2 and 3 to make 5. And then 5 and 3 will make 8, and so on. So term to term rules, this is connects the next term in the sequence to the previous term, similar to the Fibonacci one. So if we want to state the words for each sequence and to find the next 3 terms, to get from 3 to 7, we add on 4. From 7 to 11, we add on 4. And from 11 to 15, we add on 4. So the term to term is add 4 each time. And the next 3 terms are going to be 19, 23, and 27. The next one then, to get from 2 to 6, it could be add 4. But then 6 add 4 doesn't get to 18. So it's not going to be an adding on 4 time. Another way to get from 2 to 6 is to multiply by 3. 6 3s are 18, so that works again. And 18 times 3 is 54. So the rule there is multiply by 3 each time. The next 3 terms then are going to be 54 times by 3, so that's 162. With the next being 486. And the next one being 1458. To get from 32 to 16, we could take away 16, but then the next term isn't 0, so that's not going to be right. So another way to get from 32 to 16 is to divide by 2, and that works to get from 16 to 8, and it also works to get from 8 to 4. So the rule-to-rule term is divide by 2 each time. And the next 2 terms are going to be 4 divided by 2 is 2, 2 divided by 2 is 1, and 1 divided by 2 is a half. And if it's not easily recognised, it can be useful to work out the differences. So that's to find how you get from one term to the next. And sometimes the second difference can be the same. So if we think about the square numbers, so 1, 4, 9, 16, and 25, what we can see is that the first difference is 3, and then 5, and then 7, and 9. So the first differences aren't the same, so we can calculate the second difference, and then this time it's 2. So that can help us then work out the next term of the sequence. And we can keep calculating differences until they're the same, and then use that pattern to continue. So if we want to work out the next 2 terms in this sequence, what we've got is 6 to 7 is add on 1. 7 to 11 is add on 4. 11 to 18 is add on 7. 18 to 28 is 10. So the first differences are changing, but the second differences we can see are 3. So that means the next one is going to be 13. And the one after that is 3 bigger than that, so that's 16. So if we add 13 to 28, so 28 plus 13 is going to be 41. And then 41 plus 16 is 57. So those will be the next 2 terms. In example B, from 1 to 5 is 4, 5 to 10 is 5, 10 to 16 is 6, 16 to 23 is 7. So the first differences are different, so if we work out the second differences, they're each 1. So that means to get to the next one is 1 greater, so it's going to be 8. So the next term is 23 plus 8, which is 31. And then the next difference is one more, so it's going to be 9. So then 31 plus 9 is 40. So those are the next two terms. Example C, we've got 0, minus 1, minus 3, minus 6, and minus 10. To get from 0 to minus 1, we take away 1. From minus 1 to minus 3, we take away 2. Minus 3 to minus 6, take away 3. And minus 6 to minus 10, take away 4. And the difference between each of those is minus 1 each time. So that means the next one is going to be minus 1 again, so that's minus 5. And the term after that is taken away 1, so that's minus 6. So then the term after minus 10 is negative 10, take away 5, which is negative 15. And then the one after that is negative 15, take away 6, which is negative 21. So the nth term. So the nth term is a way to describe a sequence, and you can use it to figure out any term in that sequence. So it might be the first term, the second term, the third term, whatever it would be. Generally, it's called the nth term. And for linear sequences, and those are ones where there's a common first difference. So we've seen a few examples of those already. So if you've got 1, 4, 7, 10, and so on, what you're doing each time is adding 3. So if you're adding an amount or taking away a same amount every time, and the first difference is the same, then it's going to be of the form an plus b, where a is the difference between them and b is a constant that can be evaluated. And actually, if you work to the term before the first one, that's actually the value of the b. So in example 26, the first one is to find the nth term for this sequence. So what we need to do is find the first difference, and between 4 and 7, it's 3. 7 and 10, it's 3. 10 and 13, it's 3. So that means it's going to be of the form 3n plus b. As I say, to work out the b, that's the term before the 4. So if we go back the way, so we've got 13, 10, 7, 4, well, the next term's going to be 1. So that term is your b. So therefore, the nth term of this sequence is 3n plus 1. And we could use it to check. So the fourth term in this sequence is 13. So if we did 3 multiplied by 4, which is the term number, and add 1 to that, we get 13. So it seems that our formula stands up. What we need to do then is work out the 50th term, and that means that n is equal to 50. So if we do that, that's going to be 3 multiplied by 50 plus 1, which works out to be 151. So if we carried this sequence along and went from the 4th to the 5th to the 6th all the way up to the 50th, we'd find that it was 151. So the next one then, we've got the nth term. The difference, if we can see from 3 to minus 2, that's take away 5. Minus 2 to minus 7 is take away 5, and the same for minus 12 and for minus 17. So because it's minus 5 each time, that means it's going to be the form of minus 5n plus b. And to work out the b, it's the term before the 3. So thinking back in the sequence in reverse, you have minus 7, minus 2, 3. Well, the next term is going to be 8. So that 8 is the b. So the sequence then is minus 5n plus 8. What we can do is we can check that out. The minus 17 is the 5th term. So if we do minus 5 times 5, so instead of n, we're replacing it with 5, and then add on 8, we get minus 25 plus 8, which is minus 17. So that's right. Our formula then of minus 5n add 8 stands up. Now what we want to do is use the 10th term. So for the 10th term, n equals 10. So minus 5 times 10 plus 8. And that's going to be minus 50 plus 8, which is minus 42. So the 10th term is going to be minus 42. And then the last one, we've got the sequence 6, 11, 16, 21, 26. So we can see to get from 6 to 11, we add on 5. 11 to 16, we add on 5. Add on 5, add on 5. So that means it's going to be of the form 5n plus b. To work out the b, we do the sequence back the way. So we go 16, 11, 6. And the next term is going to be 1. So that means our b is 1. So the sequence is 5n plus 1. We could carry out a check. So the fifth term in the sequence is 26. So when n equals 5, we would expect 26. So that's 5 multiplied by 5 plus 1, which equals 26, which is right. So 5n plus 1 is looking really good. Then we want to see which term the sequence will equal 601. So 5n plus 1 describes the value of each and every term in that sequence. So if we say 5n plus 1 equals 601, then that'll tell us which sequence number it is. So taking away 1 from each side, we get 5n equals 600. And then dividing through by 5, we get n equals 120. So 601 will be the 120th term in the list. Now, had this worked out to be 120.4 or something like that, then what that would imply is that the term is not in the sequence. But as it worked out to be a whole number, then we know it's that term number. If we think about quadratic sequences, now we know that the linear was an plus b, and a quadratic then is a squared term. So it's going to be an squared plus bn plus c. Now what we need to do is we need to figure out the an squared first of all. Now before we get into that, I want to investigate that a little while. If we had the sequence 1n squared, that's going to be 1, 4, 9, 16, 25. And from that, the first difference we can see is 3, 5, 7, and 9. And the second difference is a constant of 2. So for 1n squared, the second difference was 2. Let's look at the sequence 2n squared. So that's going to be n squared multiplied by 2. So that's 2, 8, 18, 32, 50, and so on. And if we look at the differences between them, there's 6 and 10 and 14 and 18, and the second difference is 4. So whenever we had 2n squared, the second difference is 4. And one more we'll look at is 3n squared. So that's n squared multiplied by 3, and we've got 3, 12, 27, 48, and 75. So the first difference then is going to be 9, and then 15, 21, and 27. And the second difference then is 6, and 6, and 6 again. So whenever we had 3n squared, the second difference was 6. So generally then what we have is if you have a sequence of an squared, the second difference is going to be 2a. So if we can work out then what the second difference is in a sequence, if we divide the second difference by 2, it will get back again to the a value. So dividing 6 by 2, dividing 2 by 2, and dividing 4 by 2 tells us what we need. Then if we can remove our so many n squareds from the sequence, it will leave a linear sequence, and then we can solve that as before. So then the quadratic sequence is one where the differences between the terms aren't the same, but the second differences are. So just what we have said before. Once we work out the second difference, then the number of a squared is half of that for n squared. And that's what we've got here in this box. So always find a, first of all, using half the common difference, and then we can work out the corresponding values after that. So example 27, find the nth term of this sequence. So we've got 5, 10, 17, 26 and 37. The first difference then between 5 and 10 is 5, and then 7, 9 and 11. So the first difference isn't the same, so it means we're going to have to do a second difference. The second difference is the same, it's 2 every time, so that means it's going to be a quadratic of an squared plus bn plus c. And what we know is that a is equal to 1 because it's half of the second difference. So that means our equation now is n squared plus bn plus c. Now if we look at the sequence for n squared is 1, 4, 9, 16 and 25. And if we compare that to the original one of 5, 10, 17, 26 and 37, and if we subtract those, so if we subtract the n squared from that, what we're really doing algebraically, if we subtract n squared from that, we get bn plus c. And bn plus c is a really easy sequence. They're the ones we've looked at previously. So if we do these subtractions, then that will give us a linear sequence of the form bn plus c. So let's look at that now. So 5 take away 1 is 4, 10 take away 4 is 6, 17 take away 9 is 8, 26 take away 16 is 10, 37 take away 25 is 12. So this sequence, if we look at the first differences, so that's 2, 2, 2, 2. So that means it's going to be the form 2n plus c. To work out the number term, what we did was we went back a term. So if we go back in the sequence, so 12, 10, 8, 6, 4, the term before the 4 would be 2. So that means our c value is 2. So it's going to be 2n plus 2. So what we do is we combine that with the n squared. So our sequence then is n squared plus 2n plus 2. So find a rule for the triangular numbers. So we'll write these out first of all. So we've got 1, 3, 6, 10 and 15. So let's look at the differences. Between 1 and 3 is 2, 3 and 6 is 3, 6 and 10 is 4, 10 and 15 is 5. So the first difference isn't the same. We're going to have to look at the second. So that's 1, 1 and 1. So because the second difference is the same, it's going to be the form an squared plus bn plus c. And the link between the second difference and a is that the second difference is twice a. So that means that a is going to equal a half. So what we know then is it's going to be a half n squared plus bn plus c. Now if we can subtract the sequence a half n squared from the original one, that's going to leave bn plus c. So we've got the triangular numbers of 1, 3, 6, 10 and 15. If we think of a half n squared, so a half n squared is n squared divided by 2. So 1 times 1 is 1, divided by 2 is a half. 2 times 2 is 4, divided by, or a half of 4 is 2. 3 squared is 9, and a half of 9 is 4 and a half. 4 squared is 16, and a half of 16 is 8. 5 squared is 25, and a half of 25 is 12 and a half. So now what we need to do is subtract these. So a half, or 1 take away a half is a half. 3 take away 2 is 1. 6 take away 4 and a half is 1 and a half. 10 take 8 is 2. 15 take 12 and a half is 2 and a half. And then if we work out the difference between each of these, that's 1 half. Between 1 and 1 and a half is a half. Between 1 and a half and 2 is a half. 2 and 2 and a half is a half. So what we've got, the first difference is the same. So that's always a half. So that means it's going to be a half n plus c. And to work out the c term, it's the term before the half. So if we work back the way, we've got 2 and a half to 2 to 1 and a half to 1 to a half. So the term before that is going to be 0. So that means that C is equal to 0. So what we have then, combining the a half n plus 0 with the half n squared, is that we get the sequence is a half n squared plus a half n. What we need to do now is work out the 20th term, and the 20th term is whenever n equals 20. And if we put that in, that's going to be a half of 20 squared plus a half of 20. So 20 squared is 400, a half of 400 is 200, half of 20 is 10, so 200 plus 10 is 210. So the 20th triangular number is 210. Part C, find the rule for the nth term and the 10th term of this sequence. So let's see, we've got minus 1, 5, 15, 29, and 47. To get from minus 1 to 5, it's 6. 5 to 15 is 10. 15 to 29 is 14. And 29 to 14 is 18. So we need to go to a second difference. So that's 4, 4, and 4. So because it's 4, that means it's going to be the form 2n squared. So if we work out what 2n squared is and take it away from our sequence, so the sequence is minus 1, 5, 15, 29, and 47. And if we subtract 2n squared, so 2n squared is n squared multiplied by 2. So 1 squared is 1 times by 2 is 2. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. 4 squared is 16 times 2 is 32. And 5 squared is 25 times 2 is 50. And if we subtract those, so 1 take away 2 is minus 3. 5 take away 8 is minus 3. 15 take away 18 is minus 3, minus 3, and minus 3. So this time we have a sequence that is just full of minus 3's. So we can combine that with the original, and we know that the nth term is going to be 2n squared take away 3. So because there is no difference between the term-to-term sequence here, the nth term is always just minus 3. So we can say the first term is minus 3, the third term is minus 3, the fifth term is minus 3, the 100th term is going to be minus 3, the 300th term is minus 3, so the nth term is minus 3. Now I need to work out the 10th term of the sequence, so that's going to occur whenever n equals 10. So that's going to be 2 times 10 squared take away 3, which is 200 take away 3, which is 197. If we're given fractional sequences, then it's sometimes useful to treat these as two separate ones. So look at the sequence of the numerator, so the top number, and the sequence of the denominator. So if we look at example A then, what we can see, the numerators is 1, 2, 3, 4, 5. So the first term is 1, the second term is 2, the third term is 3, the fourth term is 4, the fifth term is 5. So what that means is that the nth term is going to be n. For the denominator, what you've got is 2, 3, 4, 5, and so on. Now, what you can actually see is that this sequence is one more than the sequence above. So its sequence then is n plus 1. So overall then, to work out the nth term of the sequence, a half, 2/3, 3/4, it's n over n plus 1. Now we could have done that with difference values. So the difference between 2 and 3 is 1, between 3 and 4 is 1, between 4 and 5 is 1, and the term before the 2 is also 1. So therefore it's going to be 1n plus 1. Example B, we've got the sequence 1, 3/4, 5/9, and so on. Now, I'm going to write that slightly differently as 1 over 1, 3 over 4, 5 over 9, 7 over 16, and 9 over 25. so that it's of the same form. Now the bottom numbers, the denominators, hopefully they're screaming out to you that they're the square numbers. So the denominator is going to be n squared. Now the top numbers are all the odd numbers, but we need to maybe figure out what the nth term of that is, that sequence is going to be. So if we think that's 1, 3, 5, 7 and 9, work out the common difference, so that's 2 every time. So that means it's going to be the form 2n. To work out how many you're adding or taking away after the 2n, you work back the way. So we go 9, 7, 5, 3, 1, and the term before that is minus 1. So that means the numerator is going to be the form 2n minus 1. So we combine the two together, and therefore it's 2n minus 1 over n squared. The last one then, example C. We've got the sequence, and again I'm going to put this as a top-heavy fraction, so that's 2 over 1, 3 over 2, 4 over 3, 5 over 4, and 6 over 5. Again, the denominator is n, so the third term in the sequence, the denominator is 3, the fifth term is 5, so the nth term is going to be n. And hopefully we can see as well that the numerator is 1 greater than the denominator, so it's going to be n plus 1. So combining those together, we get n plus 1 over n. Now again, if we weren't too sure, we could have worked out the difference between the numerators. So 2 to 3 is 1, 3 to 4 is 1, 4 to 5 is 1, 5 to 6 is 1. So that means it's going to be the form 1n. To work out what the number is, we go back the way from 6 to 5 to 4 to 3 to 2. So the term before that would be 1, which is where the plus 1 is coming from. So then combining those together, we get 1n over n plus 1 over n. Applying sequences to practical problems. So what we can do is we can apply these nth term problems to questions that we have practical applications to and real life situations. So a pattern is made out of matchsticks with a table below showing the number of matchsticks used for each pattern. Complete the table. So by looking at the link, so we've got 4 to 10, we're adding on 6. 10 to 16, we're adding on 6. So it looks like we're going to be adding on 6 again to get 22, and add 6 again to get 28, and add 6 again to get 34. Find a rule collecting m, which is the number of matchsticks, and n. So we're essentially working out the nth term this time, or again. So the nth term, because we're adding on 6 each time, that means it's going to be the form 6n. To work out how many we're adding on or taking away, we go back the way. So we've got 34, 28, 22, 16, 10, 4. So the term before that would be minus 2. So we've got 6n minus 2. Now this tells us how many matchsticks there are. So we say that m is equal to 6n minus 2. So if we were looking at pattern number 6, so if n equals 6, the number of matchsticks is 6 times 6 take away 2, which is 34. Part C, how many matchsticks are needed for the 20th pattern? So in that, n equals 20, so m is going to equal 6 times 20 take away 2, which is 120 take away 2, which is 118. And D, what pattern number will use 178 matches? So we know m is 178, so we can say that 178 equals 6n take 2. Adding on 2 to both sides, we get 180 is equal to 6n. Divided by 6, we get 30 equals n. So it's going to be the 30th term in this sequence. Here's a tile, so it's a hexagon shape. below is a sequence of patterns made from these tiles. So pattern number 1 is made up of 1 hexagon. Pattern 2 is made up of 7. Pattern 3, so we've got 7 before, and then 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So to try and make a link, it's good to draw a table like we did before. So if we have the pattern number, which we're going to call n, and the number of tiles, let's call that t, then we can draw a table and hopefully work out. So in pattern number 1, there was 1 tile. In pattern number 2, there was 7. And in 3, we said there was 19. So let's see what it would be for 4. So there's the next pattern. It's not very nice, but anyway, we've got 19 made up before, and then we've got 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. So then there's 37. So let's look at the differences then. Between 1 and 7 is 6, 7 and 19 is 12, 19 and 20 and 37 is 18. And the second common difference then is 6. So because the second common difference is 6, that means it's of the form 3n squared. So we've got the sequence 1, 7, 19 and 37. If we subtract 3n squared from that, so n squared multiplied by 3, so the first one, 1 squared times 3 is 3. The second one, 2 squared times 3 is 12. And then 3 squared times 3 is 27. 4 squared times 3 is 48. And if we take that away, we get minus 2. 7 take away 12 is minus 5. 19 take away 27 is minus 8. 37 take away 48 is minus 11. The difference between these numbers, so take away 3, between 5 and 8, take away 3, between minus 8 and minus 11 is minus 3 again. So that means it's going to be minus 3n. And then to work out the term before that, so let's go back the way, minus 11, minus 8, minus 5, minus 2. The term before that is going to be 1. So then it completes it with plus 1. So the general term number, or to work out the number of tiles in a pattern, is 3n squared minus 3n plus 1. We need to see how many are for pattern 10. So if we substitute n equals 10, we're going to get 3 times 10 squared minus 3 times 10 plus 1. 10 squared is 100 times 3 is 300. Take away 30 plus 1, which is going to be 271.